Hi friends, our next topic is wave optics. This chapter is all about wave nature of light. First of all, let's get introduced to some terms. A wavefront is a locus of points which oscillate in phase. So you can say that wavefront is defined as a surface of constant phase. So in this figure, whatever circle is you can form with this center, that will be a wavefront, any circle. So energy of wave travels in a direction perpendicular to the wavefront. Hope this is clear. If you have a point source which gives light rays in all the directions, then the locus of points which have same amplitude and vibrate in same phase will be sphere, right? So if you form any sphere with this source as center, that will be a wavefront, and this is a spherical wave. This is a spherical wave. And if you are seeing a spherical wave from a very large distance, a small part of it can be considered to be a plane. So that will be a planar wave. So there is something called as Huygens principle. Don't read this, first listen to me. The Huygens principle says that every point on a wavefront acts as a source. So this is a source, this is a source, every point is a source. So it gives waves in all directions, right? So form spheres using these points as sources. So if v is the speed of that wave in that medium, after time delta t, vt will be the distance traveled, right? So form a sphere with radius vt with all these points as centers. And when you join all these spheres by a tangent, that tangent is the new wavefront after time delta t. That is what is Huygens principle. So here it is straight, or here it is a plane, right? So here also it is a plane after time delta t. Here we started with a sphere. Take this point, join all the wavelets with a tangent, that will be again a sphere. So this is your new wavefront after time delta t, which is also a sphere with common center as well. Now there is one drawback for this Huygens principle. It says that every point acts as a new source, right? So there should be some waves coming in this direction also. But actually there are no back waves, and that is better explained with wave theory. However, this is one drawback. Let's move forward. Let us see how a plane wave refracts using Huygens principle. First of all, AB is the plane that is coming. Okay. First of all, this ray A gets refracted in this way before B falls on this plane. So first of all, when A was here, B was here, right? And then first A gets refracted because A came to the point of contact first. And afterwards, say it took time t to reach this ray from B to C. And by the time t, this ray would have traveled some distance inside this medium 2, right? And let that be R. Actually, that will be V2t, because speed of that wave, that light ray in the second medium is V2, and so it will be V2e, which is nothing but AE. Let the angle of incidence be I and the angle of refraction be R. Observe one thing. So according to my Huygens principle, when I join E and C, which are the points of those respective rays after time t, I should get my refracted wavefront. So this is my refracted wavefront. Note that it is tilted because of the refractive index of the second medium. Now I'll try to formulate this one. Observe one thing. If this is angle I, this angle is 90 minus I. So this angle is again I. What is sin I now? From right angle triangle ABC, sin I is BC by AC. Well, observe one thing. This angle is R, right? So this angle will be 90 minus R. And from right angle triangle AEC, since this is 90 minus R, this angle will be R. And from the right angle triangle AEC, what is sin R? Sin R will be AE by AC. Now, what is BC? BC is nothing but V1 into T, right? T is the time and V1 is the speed in first medium. Let it be AC here. And AE is what? V2T, we just discussed now. and here it is AC. So when I divide these two equations, I get sin I by sin R as V1 by V2. Observe one thing. If R is less than I, it means that the ray is bent towards the normal, and that means that it is the medium 2 is denser than medium 1, right? So if R is less than I can say that V2 is less than V1. So I want to say that the light ray travels with a lesser speed in a denser medium. And you know that refractive index of a particular medium, N1 say, is given by the ratio of velocities, where C is the velocity of light in air or vacuum by velocity of that light in that medium. And similarly, N2 is given by C by V2, right? So when I divide these two equations, I can get V1 by V2 as N2 by N1. So I can write V1 by V2 is equal to N2 by N1 here. And this is what? This is nothing but Snell's law. We have discussed it before, right? N1 sin I is equal to N2 sin angle of refraction. And a wavefront is what? Locus of points which are in same phase, right? So here A and B were in phase. So they should be in phase at E and C also. So if this distance should be equivalent to some phase angle, say 2 pi, that is one complete cycle, then this should also be equal to that phase angle 2 pi. And what can we say from that? Definitely A is not equal to BC. It means that the wavelength has changed when it transfers from one medium to another. Let the wavelength be lambda 1 here and let it be lambda 2 here. If I say that BC corresponds to that distance which is equal to 2 pi phase, then I can say that BC by AE is nothing but lambda 1 by lambda 2, right? And I know that BC is nothing but V1T and AE is nothing but V2T. So when TT gets cancelled, what can I say? Lambda 1 V2 is equal to V1 lambda 2. Or this can be written in another form as V1 by lambda 1 is equal to V2 by lambda 2. Speed by wavelength is nothing but frequency. So frequency in first medium is equal to frequency in second medium. It is frequency that is unaltered. This is when the plane wave travels from rarer medium to denser medium, right? When it is the reverse, what happens? Same thing, but the directions get reversed. That's it. So if this is your initial plane wave, your final plane wave will be this one. If this angle is less than the critical angle, you know what is critical angle? If the angle of incidence is more than critical angle, when the ray goes from denser to rarer medium, total internal reflection takes place. So if this is greater than IC, there will be total internal reflection. So that case would be different, and that will be similar to normal reflection case. Whether it is mirror or a total internal reflection case, it is the same. Just the reflection is the concept here. And even here, by the same principle, first of all, it was A here and it was B here. This is the plane wave. And by the time B reaches C, A would have traveled D in this direction, and it follows normal laws of reflection, that is the angle of incidence should be equal to this angle of reflection, and hence you have final wave or final plane wave in this direction. And by symmetry you can say that this angle equal to this angle and this angle is equal to this angle and everything like that. And this is how a plane wave changes when it passes through a prism, because here it travels less distance through the prism when it compared to here, right? So this part of wave lags behind, and similarly you have this wave undergoing refraction through this convex lens, and this is your final wavefront. Note that every light ray from this initial plane wave obeys this those formulas which we discussed in the last chapter, ray optics formulas, and hence you have this. Note that this point lags behind because it has to travel much distance through the lens, which is the thickest part of the lens, that is the center. And similarly for reflection of concave mirror, this is the final wavefront, whose center is the focus. If source moves away from the observer, the wavefronts which are released later have to travel a greater distance to travel to you. Got it? So they take longer time also, and hence the time period between each wave is increased when compared to that case where source is not moving and observer is not moving. So what does it mean? Time period increases means frequency decreases. For this case, when source is moving away from the observer. And similarly, when the source moves towards the observer, you have increase in frequency. That is, you perceive a greater frequency than the actual one. This is known as Doppler effect. And Doppler effect is not only for light rays, it is for any waves actually, say transfer waves, transverse waves, longitudinal waves. I mean, sound is a longitudinal wave, right? Consider this situation. Say a music concert is going on in a stadium, and you are coming from here in a bike or car, say. If you are moving with a greater speed, then you actually listen to a higher frequency than emitted by the speakers by Doppler effect. Or in musical terms, I can say you hear a higher pitch of that song than the actual one. This is because of Doppler effect. And when you move away, you hear a lower frequency. And that is because of the relative motion between the source and the observer, and that effect is more pronounced if your speed or the relative speed between source and observer is comparable to the actual wave speed. That is why you can observe this one in real life, but experiencing a Doppler effect in case of light is very difficult because speed of light is very much, right. In case of light, the typical example can be this one. Say you are observing through a telescope a distant star which is emitting light rays. So, because the star is moving, you observe a Doppler effect there. So, if it is moving away, you are going to experience a decrease in frequency. And decrease in frequency means increase in wavelength. So, it appears that you are perceiving a light of greater wavelength. So, your light ray or the light ray which you are seeing tends to shift towards the red because red is having the highest wavelength, right? That's why astronomers call it as redshift. This decrease in frequency, and when the light or the star is moving towards you, you experience a blue shift, which is the increase in frequency. And how to calculate it? It is given by delta frequency by actual frequency is equal to minus v radial by c, where c is the speed of light and v radial is the relative velocity between the source and the observer. And since you should get a decrease in frequency when the star is moving away, right? So if the source is moving away, take v rad to be v radial to be positive, and if the source is moving towards you, take it to be take v radial to be negative. And this is valid only when your relative velocity, that is v radial, when it is very less than c. Observe that. Let us solve a small problem. With what speed should a galaxy move with respect to us so that the sodium line at 589 nanometers is observed at 589.6 nanometers. So this is the increase we expect, and you know that frequency into wavelength gives speed of light, right? This is fixed. So if this changes, this should change. Okay, my frequency can be expressed as c by lambda. So d frequency by d lambda should be minus c by lambda square. But what is my c actually? It is frequency into lambda. So I'll write this one as like this square, and this one gets cancelled. So I got d frequency by frequency is equal to d lambda minus d lambda by lambda. So this is the golden equation. I know that d frequency by frequency, that is delta frequency by frequency, is given by minus v radial by c. So I'll put the same thing here. What I'll get? V radial by c is equal to change in lambda by lambda. So my v radial should be equal to speed of light, that is 3 into 10 power 8, into change in lambda is 0.6 nanometers by lambda is 589 nanometers. Finally, the answer is 306 kilometers per second.